Okay, here's a review of a FRQ question from 2009 on acids and bases. My students recently answered this question, and I want to go over some of the things that went well and other things that did not go so well. The instructions are shown here, and these are the actual instructions from a released item. It says, number 1, clearly show the method used and the steps involved in arriving at your answers. Some of the students did not use careful techniques when writing down their calculations. They were missing units. Sometimes units didn't cancel. Sometimes there was no sort of logic as to where the calculation fit in. It was just kind of scrawled on the side somewhere. I don't think a scorer would appreciate that. If you got the answer right, you're probably okay, but it's best to be careful and clearly mark your, show your work. It does say attention should be paid to significant figures, and in several cases students did not, so they were using the wrong number of significant figures in their answers, and more importantly, they oftentimes did not carry an extra significant figure during their intermediate calculations, and I'll point out when that happened. The other thing that I observed was that some students answered the questions directly on the answer sheet rather than on the answer they answered it on the question sheet rather than on the answer sheet that was provided. I don't think that would work at all in an actual test situation. So when we do this again, be sure not to put the answers right under the question. You have to give everything on the what they call the booklet, which for us would just be a piece of paper. Another thing I observed is that some students did not correctly label what number they were working on. So if it's number 1, be sure to write number 1. And they use a lot of weird numbering systems, right? So when we go down here, we're on 1D part 2. So just use the same system they use, but be very clear. It would be a real shame to get the answer right, but nobody knows which question you're working on. So let's be careful when we do that. Okay, let's go to the first question. Answer questions 1, 2, and 3. The section 2 score weighting for each question is 20%. So fine. Okay, you've got a 14.85 gram sample of the weak base ethylamine, and it's dissolved in enough water to make 500 mils of solution. Now they're going to ask you a series of questions, and usually be aware that they always are quote-unquote leading you down the garden path, meaning that the answer to A will probably show up as being important to answer B, etc., etc. So let's go ahead and answer this. Calculate the molar concentration of ethylamine in the solution. Well, that's just stoichiometry, right? You've got 14.85 grams. A certain number of grams is a mole, 40 or so, let's say. So we have, I don't know, a third of a mole. And molarity is moles per liter. Molar concentration, that means moles per liter. We have a half a liter, so I guess it would double since it's over 0.5 liters. Let's take a look at the key. And there it is. Calculate the molar concentration of the ethylamine in the solution. And 14.85 grams, but 45 grams is a mole. This should cancel nicely. On an actual test, I'd draw a nice clean line through the unit and the label, grams of ethylamine. Grams of ethylamine cancels. Now, almost all students, actually, there was only one student that carried along an extra sig fig in this calculation. This has 4, this has 3, so we're going to answer to 3 significant figures, but for an intermediate, carry at least 1 extra, and that's what they did. See how this one has 4? You could lose credit if you don't do that, so let's be more careful about that. If you don't do that, you're going to get 0.658 rather than 0.659. Will they mark that as wrong? I kind of doubt it, but you don't want to lose points because of a silly error like that. So now they calculate the molarity. It's moles over liter. So like we said, that ends up doubling, and you get a 0.659 molar solution. I had a lot of students write the answer as 0.659. They didn't have the capital M, which is, you know, potentially alarming. They could take that point off. So that's the answer to 1A. For part 1B, they tell you that the aqueous ethylamine reacts with the water according to the equation below. So they're actually giving you the exact equation, and they simply want the equilibrium constant expression. And we know from the past 2 units that that's the concentration of your products over the reactants. Coefficients become exponents, and omit solids and liquids. And we do have a liquid here, so it will simply be this concentration times that concentration divided by that concentration. I think all students got that right. And that's your case of B. Let's go to 1C. They ask us of ethylamine and the cation, that is the product, which is present in the solution at higher concentration at equilibrium, and justify your answer. The correct answer is that you're going to have a lot more reactant only because it's the Kb of a weak base, so it's going to dissociate only slightly, and there's really not much more to it than that. So let's take a look at what they say. Ethylamine is present in the solution at higher concentrations at equilibrium. That's because ethylamine's a weak base and has a small Kb. So there's nothing fancy to this. If small Kb, it doesn't dissociate much. So they say there's only partial dissociation. Some students said it doesn't dissociate totally. I don't think that's enough. You really want to say it only dissociates a little bit. And therefore, you're not going to have a lot of the positively charged ion. And that's it. 1 point for correct answer with justification. You know, if you got it right, and it would be hard for them not to give you the point if you got it right and your explanation was just decent. I think they'd still give it to you since they're not dividing it into half points. But that's the textbook answer for that. Now in part D, they say in a different solution, we make it by mixing 500 mils of 0.5 molar ethylamine with 500 mils of 0.2 molar HCl. We assume the volumes are additive, so the total will be 1 liter. The pH of the resulting solution is 10.93, and the first question they say is calculate the concentration of OH minus in the solution. Now at this point, a intelligent, hardworking AP student could go in all sorts of weird directions thinking about this, noting that it looks like you have excess ethylamine, thinking about what the balanced chemical equation would be, and when they do that, there is no OH minus as part of that, and you'd be saying to yourself, wait a minute, it's going to form NH3 plus what? You know, that's it, plus the Cl minus, that's a spectator ion, etc., etc. But maybe a smartest approach to this would just be say, well, OH minus, can I get that easily? Yeah, you got the pH, so from pH we know those formulas that can get us to OH minus. You could do the POH is what, 3.07, and 10 to the minus POH is the OH minus, or you could do it from other ways. The negative log of the pH is the H plus, and then figure out the OH minus. Then, so you could do it that way. So maybe the best approach here is just, if they're asking for it, give it to them. So, and that's what they're asking for, so go ahead and do it. And so here we have part D, calculate the OH minus. There it is. The first way they did it was first finding the pH, and then finding the OH minus, knowing that H plus times OH minus equals 10 to the minus 14th, and there it is. Or you could do it from the POH way. Either way, you get the same answer, and you got a point. Now, why they're asking you for that, you may not be quite sure yet, but then let's see where they're leading you to. For part 2, they say write the net ionic equation that represents the reaction between ethylamine and HCl. Well, in its full sense, ethylamine plus HCl will make ethyl ammonium chloride, right? It'll make C2H5NH3 plus Cl minus. Of course, it's an aqueous solution, so here it is showing instead of using H plus, you're using H3O plus because H plus gloms onto water to make H3O plus, so this is acceptable. Ethylamine plus H3O plus will form the positively charged C2H5NH3 plus, and showing this way would be showing H2O as a liquid, which you would omit from the K equation anyhow. If you had just said H plus, you'd get the same answer, right? You could just get NH3 plus, and so that you could write it. Now, they are only accepting this one, which is a little worrisome, so I think that's something to note. Given a choice between using H plus and the hydronium ion, H3O plus, always use the hydronium ion. But let us continue with where they're going from here. Now they say find the molar concentration of ethyl ammonium cation that's in the reaction. Well, let's see. Most students did not get this answer correct, but all it is really is a balanced chemical reaction where you have a big excess of the ethylamine and not as much of the H3O plus. So if you just treat this like a plain old chemical reaction with a limiting reactant, you can see that you have a lot of excess ethylamine. You have 1/4 of a mole of ethylamine, you only have 1/10 of a mole of the H+, so you're going to have 0.15 moles of ethylamine left over. Fortunately, the total volume of the solution is liters, so when you divide by liters, it doesn't change. So all these numbers that are for moles are the same number for molarity. So you're going to end up with 0.15 moles per liter of ethylamine reacting, left over, I'm sorry, and you're going to only form 0.1 moles of product, since you only have 0.1 moles of the limiting reactant, and it's a 1:1 mole ratio. This is shown on this equation. This is shown using a nice table here, but you don't necessarily need to do it that way. So you can only make 1/10 of a mole of the product, and it's in 1 liter, so its concentration is 0.1 moles per liter. So that's part 3. So that's what would happen if you did this reaction under these unusual amounts. And then in the final question, they say find the Kb for ethylamine. Now that's a little strange, but you could just go ahead, because you know why that's a little strange is because that's not the way normally people would find the Kb for something. To find the Kb, you'd just have it react in water to form NH3+ and OH-. If you check the pH of that solution, you know the initial concentration of the ethylamine. You know that for each molecule of the positively charged C2H5NH3+, that's the ethylammonium cation that forms, an equal amount of the hydroxide will form, so the concentration of OH-, which you get from the pH of the solution, will be the same as the concentration of the ethylamine. The bottom number will be assumed, which would be simply the reactant, which is ethylamine. Well, you made that to a fixed concentration, and we would use the quadratic assumption to say that it hasn't gone down by much. 100 K is less than A, for example, and you'd solve it this way. Here they're having you find out Kb based on the reaction of a base with an acid, and they didn't even do it under stoichiometrically proper conditions. They had an excess of the ethylamine. However, if you just take that chemical reaction, right, if you actually just take the Kb, not the chemical reaction, but if you actually take the Kb setup, you'll find that it's all there, right? And so you could use that data, plug it in, and you get a very low value, which seems reasonable for a weak base, and that's how you answer the final question.